Okay, folks, today let's talk a little bit about groundwater. So how is it that water can flow through the ground and then come out of this, what looks like a solid rock face as these streams? Excuse me, as these springs. So springs originate from groundwater, but where does groundwater come from and how does it move through Earth's subsurface? We'll talk about the basics of groundwater here first, and then we'll move on to some specifics about terms that you may have heard, including porosity, permeability, and aquifers. And then we'll talk about humans and their relationship with groundwater. First, let's take another look at that hydrologic cycle that we've seen before. And so we've seen these fluxes written out before, right? We've seen runoff and we've seen evaporation, precipitation. But there's one that is somewhat poorly constrained in terms of the amount, and that is called infiltration. And so infiltration is the flux that takes water from surface water and adds it to groundwater. On this map here, we can see a cross section of the subsurface, and we can see part of it is dry, but a lot of the subsurface is actually drawn as being wet. So in that ground there, so those layers of sediment and rock underground here, those pore spaces, any small gaps in the rock, are filled with water. And that is where groundwater sits, in pore spaces inside rocks and sediments under Earth's surface. Those are recharged by infiltration, and then some of it exits into surface water, like lakes and rivers, and some of it enters directly into the ocean. So if we look at the processes that are involved, so precipitation hits Earth's surface, and then that rainwater, some of it runs off the surface directly into streams, but lots of it infiltrates porous soil and rocks and flows underground toward those lakes and streams. And so wherever that water intersects with Earth's surface, then there's going to be surface water. And it might just be expressed as a single spring, or if it comes out over a wide area, that's where you might see a river or a lake. There are a couple zones to talk about. There's the unsaturated zone. So that's the area, the top area of most of the ground that is only partially filled by water. A lot of those pore spaces are filled with air instead. And so that is called the unsaturated zone because it isn't saturated with water. Below that is the saturated zone. In those areas, the pore spaces are entirely filled by water. And the surface that is the boundary between those is what we call the water table. So I'm outlining that here. The water table is the surface of groundwater. And it takes on a particular shape, and where that water table intersects with Earth's surface, you end up having surface water. Up to this point, we've thought about surface water as just running across the surface, but it's really integrated with groundwater because of the movement in between surface water and the pore spaces and rocks. Zoom in on just a small bit of this to look at some of the pore spaces. In the unsaturated zone, both water and air can occupy those pore spaces, but you do have bubbles of air mixed in with the pores in this unsaturated zone. So as rainwater hits the surface, it will percolate downward, and so some of these pores will temporarily fill with water, but then that water will keep going down and they'll empty again, and you'll be left with pockets of air again. And that water will flow downwards, percolate downwards until it hits the water table. And at that point, it gets added to the saturated zone. Get enough rain and that water table might rise as water gets added to it, and have a drought for a long time and the water table will fall. In that zone, the saturated zone, the zone of saturation, the water will fill all the pore spaces. In the unsaturated zone, which is also known as the zone of aeration, because there's some air present, water will not permanently fill all of those pore spaces. And so where the water table meets the surface, that's where surface water such as lakes and streams exists. And the water table often, at least in part, sort of mimics the topography of the land surface above it, but with less extreme slopes. So for example, under this system of hills here, ending in a valley, you'll often have a water table that has slightly higher under those hills, and then it slopes downward toward the river and stream where it's able to run off fast. But it intersects with the Earth's surface just at that small point where the stream is expressed. Now, in this view, we can start to see that sometimes there are more complicated things going on. Like here, we have a small perched water table sitting above a segment of rock that is not permeable. So water can't percolate down through this rock. And we call that an aquitard or an aquiclude. And in these places, water might not continue to percolate downwards because it can't find a path through those pore spaces. And as a result, you might have a perched water table. And where those perched water tables intersect with the land surface, you might have springs coming out. If you were to drill a well here, you'd probably have a successful well, but you could drill an even deeper well over here and not ever reach water. Now, if you were to drill a well over here, you wouldn't have too hard a time hitting that water because we're pretty close to the water table in those spots. So as I said, the topography of that water table, its shape in 3 dimensions, generally mimics the topography of the land surface, but with less extremes. And just like water on Earth's surface, water flows downhill relative to the water table topography due to gravity. And so that water that's up here at the top of this hill is going to have that gravitational force that is pulling it in one of these 2 directions, depending on just where it is. And as a result, groundwater does flow, albeit much more slowly than surface water, because of that force of gravity, as it tries under the force of gravity to even out. And so that causes groundwater eventually to enter surface water and run off in some cases. I'll note this here because in our next lab, you're going to have to interpret the water table level and determine groundwater flow direction. And in order to do that, you need to understand that water is always going to flow downhill, whether that hill is the Earth's surface or whether that hill, quote unquote, that we're talking about is sort of hills in terms of the groundwater topography itself. So in this map here, we're just looking at sort of a map view, and we've taken wells, say, and drilled into these spots here. And we've come up with a height of the water table in meters at each of these spots, so that we know by looking at this that the water table is higher over here and it's lower over here. Much like topographic contour lines, you can draw groundwater contour lines, and we can use those to figure out the direction of flow. And so when we're drawing those lines, we want to find points at exactly a particular height. So in this case, okay, we have a point at exactly 28 meters. And then we're looking around, do we see any other points that are listed on here as exactly 28 meters? No, but in between these 2, exactly in the middle is going to be another 28 meter point. So maybe we can start to draw an approximate contour like that. And then we're going to look for a spot where it would be 29 meters. Well, in between these 2, it would be exactly 29. And in between these 2 down here, there'd be a 29 meter point somewhere in between them, but it would be closer to this one. And so we might have a groundwater contour something like this. So once we've drawn those contours in, connected the dots, which way will groundwater flow? Much like water flows perpendicular to topographic contours, groundwater flows perpendicular to groundwater contours. So it flows from high to low, and if it's perpendicular to these, it'll be roughly in that direction there.